Well, hello and welcome to my next session about the use of Mathematica in data sciences. Today I will be talking about LibraryLink, CUDA, CUDALink, and in particular CUDA through LibraryLink. My last session was about parallelism in Mathematica, and the next natural extension and progression would be CUDA, and CUDA takes parallelism to the next level. So for today, I will first be giving an introduction to LibraryLink itself, unrelated to parallelism. Right? LibraryLink is incredibly powerful because it allows you to run C code in the same kernel space that your Mathematica kernel resides in. And then I will be giving an introduction to CUDA, and then we will be using CUDA directly through LibraryLink, which I think is the most powerful way to use CUDA from Mathematica. So, as I said, first LibraryLink, we can use it with CUDA and without, and then CUDA, we can use the CUDALink package, and we can use it with LibraryLink. Okay, so let's get started on LibraryLink. It is not based on sending and receiving packets, which is a major difference compared to WSTP or Mathlink. Today both names are used. Mathlink is the somewhat older name. It was renamed into WSTP, but it isn't really quite catching on. Many people still call it Mathlink. And with LibraryLink, the C code runs in the same memory space as the kernel. So this makes it possible to get direct memory access to the internal memory of the arrays in the kernel itself. Incredibly fast. And this makes it also possible to outsource an entire section of Mathematica code into C code and let that execute in the same memory space without having any performance hits for sending or receiving packets. There is no inter-process communication as you have with WSTP or Mathlink. And in many cases, that makes it even possible to prevent the copying of large blocks of memory. That way, the library can modify an array in place, right? You're not copying anything around, even with LibraryLink, where copies are incredibly fast. It is usually still better to modify data in place, directly in the kernel space. Of course, with LibraryLink, it's still possible to use these kernel copies, and we can also create arrays in the C code that are then copied back to the Mathematica kernel. But this is really very fast because it is just a memcopy. And for this contrast towards WSTP/Mathlink, I give a short excursion to WSTP at this point. And I start by pointing out that the first version of Mathlink from the late 80s was actually called a math talk. And I think it somewhat indicates the send-receive nature of sending packets around. Talking or conversation is on sending and receiving, right? So math talk was based on sending and receiving packets of data. And there is another big reason to still not discard WSTP. It's even possible to use WSTP from LibraryLink, and it can still be valuable because not all integer types are supported by LibraryLink. It only supports integer types up to 64-bit. If you want to use 128-bit integers, you have to use WSTP. There's no way around it because larger than 64-bit integers are not supported by LibraryLink. And Mathlink is still the foundation for the other link packages. For example, JLink, the Java link, Netlink for .NET, RLink, and so forth. So if you do want inter-process communication, then WSTP is still a way to go, right? You still get very fast communication. I'm not saying Mathlink is slow, right? But if it can run in the same kernel space, then try to avoid the inter-process communication. And WSTP is still great to call when you want to call Mathematica from a C program. You don't have to use C from a Mathematica session. Very powerful is when you have an application that is not written in Mathematica, and then you need certain computations for math or for visualizations or whatever, and then you can use one of these link products in order to call into the Mathematica kernel. I do that a lot with JLink, where I write a Java application with a Java Swing interface, but I call into JLink in order to be able to harness the features of the kernel. So it is a bit harder to program in Mathlink. It doesn't flow so naturally as you do normally with a C program. And the packet management has to be done explicitly, and it's the responsibility of the programmer. But nonetheless, judicious WSTP calls to exchange data occasionally between a C program and the Mathematica kernel is extremely powerful, including large packed arrays and sparse arrays. And based on audience feedback, I gladly give a session about Mathlink, so please leave appropriate comments if you want me to give a session about that. I give a session about JLink in one of the next upcoming sessions anyway. And the JLink then does this with the JVM in a much more simplified or streamlined manner, but it still requires you to manage packets, and with LibraryLink you don't have to manage packets. So you get immediate access to C or C++ if you already are a C or C++ programmer, or you have a library that someone else wrote. Perhaps you bought a commercial library, then you can use it directly with LibraryLink. So if you want the raw speed and you know that your algorithm works in C, then LibraryLink is the way to go. Also make sure your algorithm is okay with primitive types, or you can use the structs that are provided in C++, right? It is a little bit more narrow. It's a little bit more limiting compared to Mathlink, but again, you get all the power of the entire C universe and don't have to manage packets. Okay, the rough structure, and I like to show these things in a schematic diagram. When you write C code that you want to use with LibraryLink, in my way of thinking, it consists of three parts. There's one part at the top where you extract your inputs from the LibraryLink objects. It's a C++ object that Wolfram Research provides, and you extract your data from that. I call that block 1. And the second block, you can now knock yourself out. You write your C code, you write your algorithm. This goes into the middle part where you can do whatever you want in terms of your C code, your algorithm, using the data that was handed in block 1. And then at the end, what you have to do is that you need to now put your computed data into a LibraryLink object so that it can be returned into your Mathematica session, right? Retrieve the data, manipulate it, do something with it, and then bring it into the appropriate form so that it can be returned. And the example that I want to show you today is the Floyd Warshall algorithm. And what Floyd does is it finds the all pairs shortest path solution. So we don't have Floyd in Mathematica despite all the other wonderful network flow optimization functions. Floyd is the way to go when you have a dense matrix for your graph. Floyd is O of n cubed, that the cardinality of V is n, and that's the number of nodes that you have, and it's the preferred solution for dense graphs. For sparse graphs, it's usually better to use a one-to-one or one-to-many algorithms, for example Dijkstra or several other algorithms that are much better. Dijkstra is probably the most popular, but it is not the best algorithm. There are several others that can beat Dijkstra and also allow for negative arcs. The advantage here is that one could in principle run the one-to-one and the one-to-many algorithms in parallel. So for sparse graphs you would be using something else, but for dense graphs you would be using Floyd Warshall. So let me give you a simple example. We start with a network that looks like this. We have a source 1 and we now have several nodes, and we have weighted arcs, and the weight on the arc is the cost. That can be a distance, or that can be any other type of cost. It's usually called a distance or weight. It basically means the same thing. Think about it as a cost, right? A distance is a cost, a weight is a cost. So think of these as costs. And you see that not all nodes are connected. And in that case, we say that the cost or the weight or the distance is infinite. So for example, for 1, we can go to 3 and we can go to 2. But we cannot go to 5 or 6 directly. We have to go through other nodes in order to get there. So let's set this data that we have here, and then let's run it. So for example, 1 to 2 has a cost of 6. 1 to 2 has a cost of 6. You see the arc weight is 6 here. From 1 to 3, the weight is 4. That would be this arc here. And from 4 to 6, for example, would be 7. To go from 4 to 6, we have 7. Right? This is a sparse representation, but we are quickly getting to a dense matrix when we consider the costs of infinity for the arcs that we don't have in there. And many graphs are dense, not necessarily this one here, but many graphs are dense when you consider the possibility that every node is connected with every node. Okay, so we compute this, and I don't want to go too far into the Floyd algorithm. I just want to briefly say that at the beginning we are saying that all the costs are infinity. That's just what we start with the empty matrix. The empty matrix then we fill with infinity for everything. And we want to set the weights when we have an arc, and this would be #11, #12. Then we want to use that arc weight. So we're overwriting infinity with a weight that we have. And Floyd is also based on a predecessor matrix. And here we're saying that they all are set to 0 initially. This is important, and we're only doing this as a first step to set everything to 0. And then we are overwriting some values in there. So for every arc, we are saying that the predecessor of that arc is the left node, the node that we start with. It's the start node, not the end node, right? And this is what we're doing here. We are overwriting these zeros in those cases where we have an arc where we can set the predecessor. So in this case, that's relatively simple. So here you can see that we have a lot of weights of infinity. Some of them are overwritten by actual arc costs, and here we have the predecessor list. And the way to understand it is that for the start node you take it as a row, and then the column represents the end node. So for example, this is in the first row in the third column. So the predecessor of the arc from 1 to 3 is 1, right? And that is clearly the 1 here. And from 4 to the last one, for example, we take the 4th row, the 6th column. That means the predecessor in the node from 4 to 6 is 4. Okay, so we're just storing the weights and the predecessors here, because that's what Floyd Warshall needs as input. And then we're running it, and let's look at the solution matrix, which really means the cost matrix and the predecessors. So the way to understand it is that, again, we start with the row first for the start, and then by column. So for example, to go from 1 to 4 would be a total cost of 5, because we go the shortest way to get from 1 to 4 would be to go from 1 to 3 at a cost of 4 plus 1 from 3 to 4. All the others are possible, but they are not as short, they're not as cheap. If we go from 1 to 2, that's 6 plus 2. And if we go from 1 to 3 to 5, that's 4 plus 2 plus 1. So the shortest distance is going 1, 3, 4, right? And this for a total cost of 5. And this is what we see here. and to actually get there. So now we start at the end and work our way backwards. So for example, from 1 to 4, we start here. The 1 represents the row, the 4 represents the column, and that means the predecessor is 3. And it is, right? When we start at the end, the predecessor is 3. And next, what we do, we now are in the same row and go in the 3rd position and look for the predecessor. That's 1. And indeed, the predecessor of 3 is 1. And then we go on the 1st column and we get a 0 and we're done, right? This is the way to indicate, the 0 is the way to indicate that we are done. We found our start where we wanted to start our path. Okay, so I've written a function here that finds us the path. We're going in reverse because we're starting at the end of it. We're using predecessor lists, so we're starting at the end and go forward. So at the end we have to reverse it. So we start with an empty path, and if the start node is the same as the end node, then we don't really have a path. Or when in the predecessor list we get a distance of 0, then we're done. And until that is done, we do a while loop where we are always finding the predecessor until we find the 0, because then we're at the beginning of the path that we're looking at. Okay, so when we look at this now for the whole matrix, I'm using tuples with comma 2 to get all the possible arcs that are in the graph. And then we see, for example, that from 1 to 1, we have a distance of 0. We can't really call it a path, so I'm saying no path possible. To go from 1 to 4, we go 1, 3, 4 for a distance of 5. That's what we had already looked at, right? And so then we can see all the distances, whether or not they're possible. In the last column, I have a 0 when there really is no path, and I have infinity when the path is not possible. And for example, from 3 to 1, there is no way to get there. This is infinity. We can't get from 3 to 1. If we look at this one again here. Here's 3, here's 1. How do you want to go from 3 to 1? You can't. The arrows do not make it possible. In that case, the last column here shows infinity. Okay, so this is the basics of the algorithm, and let's look at some larger examples. Let's look at a graph that is generated with the coprime function. I like this graph for several reasons. One thing is that for the cost structure that I'm about to set up, we have a main diagonal where there is no node, right? We're using coprime, so what do you expect? Coprime of 5 and 5. We are simply getting an empty diagonal except for the point 1, 1, except for this node here that we have at the beginning. And it also has several white areas here in between. If you look closer, then we see there are some areas where dots are completely missing. And we also have entire rows and columns where we have only an occasional dot. Look, for example, at row 42, right? This is mostly empty, but occasionally there's a dot. So this provides for an interesting cost structure when I'm showing you this in the example when I go through it. A note to self. So not with 10, but maybe something smaller. I generally like to throw a call out in front of the expression simply because it may help you understand the point structure. What if you don't know what these points are? What if you want to really see closer what the nodes are, what the points are? So I sometimes like to just throw a call out in front of it and see what I'm dealing with. All right, so let's get back to our grid with 60 by 60. And now let's fill this. Let's compute these coordinates. Let's generate the exact coordinates for the nodes. And now what I want to do, I want to allow only those distances where the Euclidean distance is exactly 1. That means for every point only the right neighbor, the left neighbor, or the one above or the one below. Right, so there's only 4 possible at most. Maybe there is no neighbor, but not a diagonal. That would be square root of 2. And when I do this, I create a cost structure that should be fairly interesting for the analysis in a moment. And I want to point out that sometimes in a select, it can be sensible to do a pre-selection first. So here in this case is where I do a structural match, where I check only the neighbors that are right, left, up, above and below, right? It's like north, south, west, east. Then you can save a lot of time when you do a pre-processing and then only the result goes into the select. Cases is a structural match, so it's very fast in these simple cases where we're just taking a difference and taking the length less than or equal to 1. That makes it faster for this select here. Okay, so we have our selections, and let's run our Floyd Warshall algorithm. I make a separate one just for the timing result. This should take something like 15 seconds or so, and we can see that the CPU is at 100% here for this run, and we are finished after about 19 seconds. And when we run this, then this code gives us the solution matrix and the predecessor matrix. So they're now fairly big, so I don't want to clutter the screen with that. It should be fairly large. N is a fairly large number here. And the reason I think Floyd is used for this is because it's O of n of 3, right? N cubed. So for these large numbers, we really are getting a great performance in C, and this would be significantly slower if I were to write this in Mathematica. Feel free to prove me wrong. Write the same thing write the Floyd algorithm in Mathematica. I'll show it to you in the end and leave a comment, right? But it's O n of 3 and we have 2100 nodes. So it's a lot of runtime, it's a lot of complication, a lot of computation that is going on here. When we look at this, I get 10.1 billion elements that have to be handled in an n raised to the third power, O n of 3 algorithm. Okay, so find path we already have, and I have to do a while loop to take random integers because not every point actually has a node. Here's a fairly long one, and then we can display it, and we see we have got a fairly long path here. And a reminder, when the distance that is permitted is exactly 1, then you cannot go diagonal. So everything here has to be on straight lines, right? Sometimes called the Manhattan norm, because everything is just with these 4 cardinal directions: north, south, west, and east. So that means when we have one node in the upper left half and the other node in the lower right half, and the probability for that is about 50%, then the only path to connect them is through this one point here, this 1 point in the lower left, because there's nothing on the diagonal. And we only allow distances of exactly 1. Now, the solution of Floyd Warshall in these cases is not unique. There could be other possible solutions, but it gives us one possible solution, and we can do this a few times and look at some of these outputs. Yeah, here's another one that goes through the point 1, 1. The probability is smaller when you are trying to find a path in just one side. The probability for that is now down to 25% or somewhere there. Here we have one, right? So this is, I think, an interesting geometry and shows that Floyd Warshall, like all the combinatorial algorithms, are quite useful for discrete problems as well. That also makes them very amenable for artificial intelligence. But it's important how you construct your weights. It's important that here we said we select only those where the Euclidean distance is exactly 1, and then we fill up our matrix with these costs. Okay, so more on this geometry. So I think the longest path possible here is from one of these two nodes to the other one. We have to go all around the entire graph, because we have to go through 1, 1, right? They're so close. The distance between them is really fairly close, but we have to go the whole path around because we only allow distances of exactly 1 and no more than 1. And for a diagonal, we always would need more than 1. Okay, some other interesting consequences. Here's another one where we have two nodes that are fairly close together, and the only way to make this connection is to go through this entire circle there, this entire rectangle. And another one here, they're fairly close, the distance is only 2, but we have to go around this entire rectangle. I want to remind you of the function monitor, and I wait 5 seconds before I go to the next one, right? You see this pause 5 here. So with monitor, we can specify a symbol that we want to monitor, in this case LP for the list plot. So every 5 seconds, we are now getting a new random pair and can look at them with monitor. All right, so I don't want to spend too much time on the application. I just want to show you that writing this in LibraryLink can be incredibly powerful and make things faster than it would be if you were just using Mathematica code. So when we're done with this, it should stop any moment. Yeah, let me show you the code. It is really just this three-dimensional loop. We have to go through all the nodes for the start nodes. We have to go through all the nodes for the end nodes. And we always need to go through a middle node that stores the entire path that we're currently looking at. We're always comparing the current situation that we have if something else that goes through the loop, the outermost loop that is indexed with L, if that might be faster. If this is lower, well then great, let's replace what we have currently. You see that we're overwriting W of I times N plus J with the new value, and we're storing that in the predecessor matrix. Now I find it a bit difficult to set up two-dimensional or three-dimensional or higher dimensional matrices with LibraryLink, and that's why I simply use a one-dimensional vector. You can put any matrix in a one-dimensional vector and just add to the indices. You see that I always have I times N here, and here for the predecessors I just add N squared, right? Because now the index is larger by the value of N squared, which is the N by N matrix that we start with. That's where we store the weights. Well, we can write more to the same weight matrix, right? We don't have to do too much shuffling with high dimensional indices. We just have to add N squared to the indices, and also here on the right hand side, right? So this means that to go from I to J, the predecessor is now stored in this position by using L times N plus J, and that comes up here. We're simply overwriting it. We're overwriting the weight with the newly found weight that goes through another node, right? This is why this type of algorithm is called a label correcting algorithm. There are label setting algorithms and there are label correcting algorithms. And Floyd is an example for a label correcting algorithm, because we're taking the same thing that we just compared and we're overwriting the value with the newly found shorter distance. But you see it's a three-dimensional loop, and this is ideal to do in C directly. Okay, so let's pick another example. For the next example, I want to create a really large matrix where we are using all points on a 300 by 300 grid, where all the distances, the Euclidean distances, are integers, and I remove the axes. Right? You see that I delete cases where the x-coordinate or the y-coordinate is 0, so I remove the axes. So you see that there's a lot of white space here. So here to find short path should be also a little bit more interesting, because we cannot just go straight. We cannot just go direct. That would be too easy. So I'm filtering out those points that don't have Euclidean distances that correspond to an integer length. All right, so let's fill these tables here. Let's make this selection as well. And here I'm saying that the Euclidean distance must be less than 20. And this will also allow me to show you something very interesting in a moment, because it really means that the Floyd algorithm now picks the lowest number of hops that it can possibly take in order to get to that distance, right? Instead of going 1 and 1 and 1 and 1 and 1, it's trying to make as large as possible a jump. It just has to be less than 20, but we are trying to use as few hops as possible. This is what you would do when you do an airline flight where you have a connection. You're trying to make as few connections as possible, even if that means the distance you're flying is longer than if you were to make short hops, but then many hops, right? You can make 5 short flights of very short distance, but there's also a cost to the change in planes, the layover, and that's why it's a good idea to also minimize the number of hops that you have to do. So it can be faster to make it with only one layover, with only one plane change, even though that's a longer distance to fly. But why would you care, right? So this is one other thing we can see very nicely here with the Floyd algorithm in a moment. But for that I need to set a maximum distance, and we'll see that all the solutions that we're gonna get, they are trying to maximize this budget of 20 that we give it. We're not gonna see any short distances here. I think most of the distances are between 10 and 20. I don't really see distances between 0 and between 1 and 10 here. Most of them are between 10 and 20. So when we're setting a maximum distance of 20, we are really trying to fill it up, if you will, so that we use as few hops as possible. Okay, so we've made our selection, and then let's do the computation. I'll spare you the timing result, the one that just gives the timing result. Let's just go straight to the computation that gives us solution and predecessors. Now what you see here, most of the computation time is actually not the C code that we're using with LibraryLink. It is the Mathematica part that are happening here in order to give us the data and to format the data. Again, solution and predecessors are fairly large data matrices now, so I'm not going to show you them. Let's better look at some pictures. So let's look, here's a very short one, only 4 nodes, and here we are on a very short example. And you see that the distances are 10.8 and 18. Those are the distances that we have in this hub. Let's take a longer one. Here's another one. You see that when the points are lined up, we are largely trying to follow that line, but we're making big jumps here, right? Again, look at all these numbers. They're all larger than 15. There's no number here less than 15. And we have to leave this line of dots when we have to, in order to deviate a little bit to the point which is not on the line of dots. So let's look at a few of my examples here. Okay, that's perhaps not all that interesting. Yeah, interesting are larger ones that go through the center, right? Here we have one that goes straight through the center. And you see that there are all large numbers. Here the 5 is a bit of an exception. Let's do a few more. Yeah, and here you have several dots on a line, and then we have to leave the line a little bit in order to reach the source or the target. And yeah, here's a nice one. You see that due to the restriction of a maximum length of 20, we have to get somewhat to the center. There's no way around it. How else would I get there? There's so much white here in the middle between the first and second quadrant. There's no way that we can cross this big space here. So we have to get somewhat in the middle, and then we take the bend, and then we can go to the other point, the other points on the line. Here we have one where we are lucky that we can make the connection with just a maximum length of 20 per step. Right, here we are in that situation where we can actually do that, so we don't have to go so far into the center. Oh, here's another one. That one is also beautiful, right? To get from the third quadrant to the fourth, or the other way around, right? There's no direction here. We have to get to the middle because this big white area here is in the way where we just cannot make any jump because our plane has only fuel for 20 units, for 20 distance units, right? So we cannot cross that ocean here. And all right, so one could go on and on here. I find these graphs and these conclusions about these algorithms absolutely fascinating. All right, so that brings me to part 2, that is about CUDA. And I can't give you a proper introduction to CUDA. I have to refer you to some literature or video classes if you are a beginner. And if you want to learn CUDA from scratch, I can highly recommend a tutorial that was jointly done by UC Davis and Udacity. I have the hyperlink for you here. It's now a free video course that you find on YouTube. So at the beginning, I had already mentioned there's basically 2 ways to use CUDA from Mathematica. Use the CUDALink package, and I'm about to show you that in a moment. And the CUDALink package has several predefined functions that use CUDA internally. And in my personal opinion, I think the most useful function is CUDA function load. Because with CUDA function load, you can now define your CUDA kernel in a Mathematica string or in a file name. And if you do that, all you need to do is worry about the kernel. You don't have to worry about a big library or application program that runs it. You don't need a main method for it. The running program, the application, is your Mathematica session. So all you need to do really is worry about specifically just the CUDA kernel, and you can specify that with CUDA function load. It allows you to provide a CUDA kernel as a string or as a file name, and the combination and the linking is done for you by the function CUDA function load. And then you can run the CUDA kernel directly from your Mathematica session. I find this incredibly practical because there's so much work that you don't have to do. You can really focus on your kernel. That's where your real mental power is, and don't deal with all the other ceremony that you will need to do it. Unless you have a mistake in your kernel, then CUDA function load will compile and link automatically for you. And the other way to use CUDA from Mathematica is to use LibraryLink. And I actually think this is the most powerful approach if you want to write a really involved, complex CUDA kernel, and perhaps also more than just a CUDA kernel. Maybe you have several, and maybe you have CUDA kernels that also require other subfunctions or other CUDA kernel, maybe those that you don't want to publicly expose. That is called dynamic parallelism. I think with version 6.5 they started calling it dynamic parallelism. So you can use other subfunctions on the GPU. So with that, you can write powerful C or C++ or CUDA code inside Eclipse Edition. It has all the bells and whistles that you would expect from a professional development IDE. You get IntelliSense, you get a debugger, a profiler, you get a task viewer, watch variables, you get the code outline, everything, right? I mean, it shouldn't be a surprise. We have all this based on the Eclipse framework, right? So here you have the outline view, here you have your code view, you have the project explorer, there's a debugger here, there's a profiler, you also have them here, you can run them, debug them, you can profile them and specify configurations. There are run configurations, profile configurations, I think debug configurations, waypoints, breakpoints, right? I mean, basically the whole feature set of the entire Eclipse ecosystem. And I find this just a really powerful way to write your CUDA code. Basically, CUDA is C, right? It's C with extensions. And as you see here, you get syntax coloring, you get IntelliSense, you get really a lot of features that the system can directly inherit from the Eclipse ecosystem. So that makes writing easier, it makes debugging easier, you can profile. It's just very, very powerful if you really want a professional development IDE. If you use it with CUDA function load, well, then your IDE is your Mathematica session, and that's great when you have a simple kernel that fits into a string or a file name. But if you really need a full-featured development IDE, then you would be using it through LibraryLink. So another advantage is that you can also use it then to write standalone C, C++ or CUDA programs or libraries, right? Nobody says that you have to use it through Mathematica. Maybe you're writing a C or C++ application, you use CUDA in there, and then you like some of these CUDA kernels, and then you want to use just the kernels in your Mathematica session. All right, so you're not restricted to CUDA kernels with this. With CUDA function load, you are restricted to CUDA kernels. All right, and I think all the inside features are extremely well done here, because NVIDIA was able to bolt on the extremely powerful features from Eclipse. Many features could be directly inherited. So, and yeah, another side note, here we see that Eclipse is not just the Java IDE, right? The Eclipse Foundation always emphasizes that. It's not just for writing Java code. Eclipse is basically, and I think I'm using their own words, it's a framework to develop IDEs. And we see that very well here because NVIDIA was now able to custom tailor this Eclipse framework to write their IDE, right? Inside is their IDE, but it uses the Eclipse infrastructure. And yes, the Eclipse Foundation says it's a platform or an ecosystem to build IDEs. And I still want to point out that I think you would be using Visual Studio on Windows, right? I don't know much about it. I don't use Windows, but the Visual Studio version is, I think, what you would be doing on Windows. So let's start with part one, the CUDALink package. So first we need to load the package, and I have to say that there are several problems with the package. There's no way of denying it. You see that CUDA compilers immediately shows up in red, and that means that there's a context shadowing problem going on. Unfortunately, there are several issues. You also see that some functions are immediately black, so that means CUDA information is totally legit, but CUDA resources information is still in black. It shouldn't be, right? They should be all in black. So unfortunately, there are some context shadowing problems with the CUDALink package, and that's also one of the reasons why I try to avoid it. I try to use LibraryLink. Occasionally I use CUDA function load. But let's look at some of the functions as possible. So CUDA information gives you an information on your hardware, on your CUDA hardware. And I have 5 GPUs on this. I have a GTX 980 and I have 4 Tesla K80 GPUs that we have here. So with CUDA information, you can look at your hardware and all the properties that each of the GPU has. The clock rate, the compute capability, block dimensions, pretty much everything that you would like to know about your hardware, and to the extent that Mathematica understands it, right? Total memory, the K80s have the advantage that we can use 12 gigabytes here. The GTX 980 only has 4 gigabytes. We have ECC memory and so forth, right? It's a good idea to look at this and really ascertain that you have the right hardware and that the hardware meets your specs. The CUDA resources information tells you what version, basically the version of your CUDA package is. So we have version 12.0346 here. This is on a Linux 64 version. It's Mathematica 12, and yeah, the minimum driver is 290 and so forth, right? You can look up all this information, but this is now specifically for the CUDA package. The CUDA C compilers, and again, this absolutely shouldn't be in red and this shouldn't be in blue. I use GCC here, and the location and everything is here in your session. Those are the things that you should get familiar with. Probably not every time that you're programming in CUDA from Mathematica, but you should get familiar with it so that you know what hardware you're having and what your CUDA resources are. Okay, so some of these CUDA functions, one of them is CUDA map, and that now allows you to perform the map operation in GPU memory. So for example, let's create 100 random reals and let's compute the cosine of it. And the beauty is that with this, we can now perform these operations on the GPU memory, right? Not in main memory, but we can use it directly on the GPU memory. So CUDA map is a nice way to create tables, right? There is no CUDA table, but we have CUDA map in order to generate these table-like structures. This is basically a one-dimensional table. We can also fault over these operations, and fault is a very, very powerful method to process lists and compute many things based on these lists. Fault is, I think, one of the most useful functions in the Mathematica system. So for example, if we're adding all of them together, we're getting, well, almost 82, right? So it now computes the sum of all these numbers, these random numbers that we have on the GPU. And the important difference between fault and CUDA fault is that CUDA fault can work on the GPU memory, right? We can now get the memory. We do that with CUDA memory load. We put this data in the GPU memory. Mem is now the location where we have it on the GPU memory. And now we can perform these computations here directly in the GPU memory. That's why it's called CUDA fault. Because compared to fault, we only need to do a few operations now, and fault doesn't run on the GPU. It runs in your main memory. And unfortunately, we only have a few operations that are supported for CUDA fault, and they're plus, minus, min, max, and times. And that is already a lot. We can already accomplish a lot with these functions, but unfortunately, it's only these 5 functions at this time. Okay, a great way to use it, we also have CUDA fault list, is we can quickly compute, generate, visualize random walks, right? If you do some Markov theory, so we can quickly generate and visualize, for example, a Markov walk with random reals or with random integers. And if we use integers, then that's called a path on a lattice, right? Works very fast and works directly in the GPU. That's the main point. We are doing this in the GPU and not in the main memory on a CPU. So there are several other functions that are CUDA enhanced, and here is a list of them. And you will see that there's a lot of them that have image in them. CUDA is great for image manipulation, and we have a few others. CUDA dot, there are some functions that are from the realm of linear algebra, CUDA dot for example, and we have these image manipulation function and many functions just to manipulate your CUDA session or the CUDA functions that we have. Okay, I have to point out that not all CUDA package functions work on all systems. There are things that don't work here on this Linux. A friend of mine reports problems on Windows. CUDA dot and CUDA total, if I were to use them right now, they would crash my system, which is Linux 64. So you have to take this with a grain of salt. Not everything works on every system. And also the documentation is very outdated. Some things are absolutely not true anymore. So you have to take the CUDA package with a grain of salt. I've already showed you the context shadowing problems above here. So you have to be careful and really check what you're doing with it and check your results. It is not something that works flawlessly, and there are things that are just crashing things on some systems on Linux. Okay, so yes, so to proceed for the next examples, I have to kill the kernel and reload it. It's not great, but it's, I think, worth it. If you don't use too many of these functions, then you can probably get away with just using just loading the package once and then be able to deal with it. Okay, so I have to load the package again for the following. And I typically, for involved CUDA computations, I use my fifth GPU, that's device 4. So in the CUDALink package speak, which enumerates lists 1 based and not 0 based, this would be CUDA device 5. The reason I like this one most is because the fifth GPU is the coldest GPU that I have. When I look at the temperatures, the device 4 is usually the one that has the best cooling. What do we have here? 31 Celsius. All the other ones are hotter, so I'm using only the GPU 4 when I have a choice. And what's great is that we can set the CUDA device that we want to use. $CUDA device equals, and now you set your device. Unfortunately, you can only do it once for your entire session, so I cannot change this now. Once you set your device, that's for the rest of your session. That's a shortcoming. Fortunately, it's documented. It's good that it's there. It's not too great that it cannot be changed. All right, so let's look at random numbers. So we have one of the files from NVIDIA that are random.cu, and that allows us to access random number functions now. And we now load the function with CUDA function load. That's the function I had mentioned at the beginning. On Linux, unfortunately, you have to load it twice, but then it works. And on Linux, you also have to set the compiler installation. There is this option here. This shouldn't be necessary on Windows. So CUDA function load first takes the source. That's either the file or the string. Then the function that you take from the file that was provided. Here is the first, either as a file or as a string, and inverse CND is the function that we are using. So let's look at it. It should be there somewhere. Inverse, you can't see my search window here. Let's search for it again. No, these are all subfunctions. Here you would call the in. Here you have inverse CND, and you see it's a global void, so this function is publicly exposed. If you want to hide it and use it as a function for dynamic parallelism, you would use device. Okay, So this shows us the function that we end up calling, and we need to specify that in the next argument. We specify that here in verse C and D. You next specify the input types, and I use the first argument now for input and output. It will be reals. I don't care about the dimension. And I also provide an integer here that we have for the function call, and another integer that we have, and the output comes back in the first argument. Right? So the inputs are a real vector, one integer and another integer. The block size is 1024 here. You would have to look that up for your device. This is the maximum block size that I can have on this device. It's a fairly typical number. Okay, so let's try to generate a billion random numbers, and you see that we see activity on GPU 4 now. You see that memory comes up and the computation time comes up. We're really doing something here. Now the computation is done, but the red curve shows us that we still have that in memory. And you see everything is blue here, and we are retrieving the data with CUDA memory get, right? And I think a nice way to deal with a billion numbers in the Mathematica system is, for example, with a histogram. This is now fairly fast because we put these billion numbers basically just into 1,000 buckets, and the front end can deal with 1,000 items. If I were to display this list here, even if I did a short of this list, then the front end would have to deal with a billion numbers, and that will just take, for practical purposes, I'm calling it forever, right? Even if I did a short, like a short of RV, yep, don't do this. This would take forever, because even though short displays only a little bit, short first has to read in everything. So short would have to deal with a billion numbers before it can display a short list. But if we bucketize this with 1,000, display it as PDF, you see that this came fairly quickly. You now see a histogram of a billion numbers. And after we retrieve it with CUDA memory get, we still have it in memory, right? You see that we still have the red curve here. We still have it in memory, where it consumes maybe 70% of the memory that we have on this GPU, which was 12 gigabytes, and then we're using about 8 gigabytes because we want a billion samples. So we should also see this when we ask for the memory information. Right, the byte count is 8 billion, and the dimension is 1 billion on device 5, right? And we are synchronized with host and the device. So everything is good, but we're done with it now, and then you should unload the memory. You do that with CUDA memory unload, and now it frees the memory. It hasn't really made the memory empty. You see that we still have the red line here. What it basically means is that the memory is now overwritable, right? It's like deleting files on the hard drive. You normally don't really delete them, but you make the system believe they are deleted because you mark the space as overwritable. I think a better word instead of delete would be overwritable. And the memory is now overwritable, and we'll overwrite it in a moment with the next example. So another file that we have that is included in our Mathematica distribution is Black-Scholes option pricing. There is Black-Scholes _ simple. And for all practical purposes, Black-Scholes here means that we're computing European option prices, not American option prices. I think the terminology is not great when you're dealing with Black-Scholes financial derivatives valuation. Black-Scholes means something different. It means a Black-Scholes framework and the Black-Scholes partial differential equation. And I will be talking about this in great detail in my next session about financial option theory. But for all practical purposes here, we just mean the European functions. Okay, so let's load the package. And here we are now specifying that we want real output, a vector, one or more dimensions, another real output, real output, real input, real input. These are the input types, right? And you also specify the output types directly here in this interface, block size, and then you can give additional parameters. The target precision here is set to double, because when you're really dealing with financial derivatives, you do want a lot of precision, you do want correct decimals. And the Tesla cards, the K80 that I have, the 4 GPUs here, they shine in spades when it comes to double precision. The GTX cards, these are the typical graphics cards and the ones used for gaming. They usually don't have good double precision. But if the card is a Tesla grade card, Teslas are basically developed for data centers, then you have outstanding double performance. And again, we have to specify the compiler location. So these are the options that I give here. And now let's do a few computations with that. The point I'm trying to make here is that you have it directly at your fingertips already, and you can specify lists as inputs, right? What I'm specifying is that we want to have several calls that we want to allocate, and for the put we want to allocate the memory, and the current prices, the current stock prices are a list, the strike prices are a list, and the strike times to expiration are a list. So these are these parameters here, right? In the random example, I only showed you that we had a list and two integers. So we can use multiple lists here and multiple integers. And in option pricing theory, when you implement these types of functions, for a practitioner, it's usually important that you get a list of stock prices, a list of strike prices, and a list of expirations. The other things don't change in the market so quickly. The risk-free interest rate doesn't change quickly, and volatility can sometimes change quickly, but then you have to recompute everything anyway. The things that change very fast are the current stock prices or futures prices, and you normally have a lot of strikes, dozens, can be hundreds, and you normally have a lot of expirations. Usually the next month are weekly expirations, then you have monthly expirations. So these are the things that are usually provided as lists, and risk-free interest rate and volatility are typically provided as constant numbers. So let's evaluate this. Let's do the timing, and you see that the memory was now cleared because now we wanted it, right? We now want to consume the memory, and you see that now we have actually freed the memory on GPU 4, and there was the computation. Just this green blip here, it's merely a blip on the screen, and you see that the whole thing took basically no time. It took us 3 milliseconds. Yeah. Okay, and let's look at the results. And typically on an options trading screen, you have calls on the left, puts on the right, and strikes in the middle. Right? So keep in mind, we have powerful functions like this, and I showed you the long file already built in our Mathematica system. Yeah? Just load it, use it, make some specifications on how you want the computation to be done, then specify your input, and in no time you get these computations. Right? It was quite a lot actually. We've done a lot of computations on the GPU. Let's look at it. We had, well, okay, it's not that much. I didn't give it a really big problem here. I didn't really give it a big one. If you want to see this in action with a lot of data input, then watch my next session on financial options. Here we only have 64 on a byte count of 505. Okay, that was really pretty small. Okay, so for the next computation, I want to show you that we can do a lot of computations directly with these Black-Scholes functions in no time. Let's now do it with 48,000, and you see that this took us 31 milliseconds. All right, So here I'm using a lot of input. I'm using tuples just to generate a lot of these spot price pairs. And when we now look at these computations, we see that in no time, right, 31 milliseconds, we can do the computation that take much longer to display. So here you see that we have options where I'm calling calls and puts, and we're doing this with 1 hour to expiration, and we're starting at 1 day, right, counting down in 24 hours. So these are 24 curves, and this also computed us the calls and the puts, not just one of them, right? With this call we get both. We get calls and we get puts. We get this in the output, and you will remember that we had the first two as output, right? Then came the inputs. We specified that the first two are supposed to be outputs. So that's the calls and the puts. So here you see in each chart, you see 24. That is from 1 day to expiration until 1 hour to expiration. And let's plot it again. You see how long it takes just to plot this, and it takes no time to compute this, right? When we compute it very, very fast, incredibly fast. Okay, so in this example now, I want to show you that we can call CUDA memory get anytime now. We still have that stuff in memory, and every time you want to use it, just call CUDA memory get. We had properly allocated it with CUDA memory allocate for the calls and CUDA memory allocate for the puts, right? So just call it with CUDA memory get, and then you can retrieve the data as many times as you want. And I personally sometimes like these stripe type of charts because it helps me to understand a little bit about the geometry of the problem, and it doesn't consume too much memory and doesn't take too long to print. It doesn't take too long in the front end to show me what I want to look at. So if we see that it's getting a little bit more tight here in this corner, there is this nick here that we have here with the black line, and I think these type of displays are quite useful where you're making it rather dense in one dimension and not so dense in the other dimension. It consumes little memory in the front end. It's responsive. I have a zippy experience here. With a big three-dimensional plot, you don't always have that. But that's a matter of choice. That's a matter of opinion. I like sometimes these types of displays to understand better what I'm dealing with. I also like the contour plots, or in this case the list contour plots. They're usually also quite zippy. I like some contour options here, and again we got the data quickly from the GPU memory with CUDA memory get, and then we can simply display it. And again, what takes the longest is usually Mathematica rendering it. So next, what I want to show you is that we can also look at the so-called Greeks. The financial derivatives have risk control parameters that are called Greeks, and here we're looking at a delta. So I'm again using tuples to create a lot of combinations for spot prices, for times, and for strike prices. Here in this case 184,000. And let's compute everything here. 17 milliseconds, we're done, and I'm calling them here with calls plus. That's the step to the right and the derivative. I'll show you this in a moment. You'll remember from high school the way you take the derivative, right? It's function at x plus delta x minus delta divided by 2 delta x. So for the step to the right, I call them plus. And now let's compute the same thing with minus. So I call them calls plus and calls minus. Then the formula calls for taking their difference divided by 2 times the delta x, and I had 1000 here, and instead of dividing by 1 over that number, I can simply multiply with 500. So And if we want to display that, then again we have to display it by getting the data first, but I already did that here. For calls minus, I used CUDA memory get. For calls plus and put plus, I use CUDA memory get. Then here the delta takes these numbers and computes them. That didn't take long. Now the hard thing is to display all these numbers. A list plot 3D takes a lot of time when you have very dense meshing, and that's what's computing now, right? Again, remember the computation time was so fast. It's now the graphical rendering in the front end, and we now have it. And here you see our delta and a list contour plot. Sometimes the list contour plot, I think, or the contour plot shows you a lot of the geometry. You see those square roots here over the surface. There is a mathematical reason for that, and you don't see that directly in a three-dimensional plot because you don't see those elevation lines. And yeah, you see that it takes some time to rotate this. We have a initial condition that is 0 above the strike, and it is 1 below the strike. That's for calls. I'm only showing it for the calls here. For the puts, it would look similar, but the other way around. Okay, so I should also point out at this point that in real life, the practitioner usually doesn't use these types of charts and plots. That's for the researcher, the one who develops the formulas. In real life, in a trading room, people prefer to look at numbers. A trading room, a trader has tons of charts in front of him. And these are the things that need to be computed fast, is these option prices. So those are the things that we've computed very fast here with CUDA. These time-consuming things like studying now a dense three-dimensional plot, those are things that are typically not done in the trading room. So you're not losing speed when it really counts, when you really have to compute fast. All right, and in closing out the session, I should add that this is of course only for European options, and most options that trade in real life are not European options, they're American options. I don't want to go further into it. European options are faster to compute, but perhaps you can trust me, if you can do it so fast in the computation, then it's better to do this on the GPU when we have harder computations like the American options. And more practitioners switch over to using CUDA to compute the American options too. I think I should cover more about this if I wanted to show American options. So for now, I'm just using the fast European options. But it's the same story for American options. When you really want the more complicated version, you compute it on CUDA. All right? Okay, so I want to point out that we also have the ability to use symbolic CUDA code generation, and we can make this CUDA code writing incredibly powerful, because in Mathematica we can now write programs that write CUDA programs for us. So this is in principle similar to the automatic C code generation that we saw in version 8. There was a symbolic C code package available. And if you want to look more at this, have a look at symbolic C tutorial overview in the help browser. And we have something similar now for the CUDA code generation, and have a look at these symbolic functions. With these functions, you can now write Mathematica code that writes you the CUDA code. It's just absolutely fantastic. We can use the symbolic technology in order to basically have a Mathematica program write us the CUDA code, so we don't have to write it by hand. So also have a look at this. I don't have time to look at this in this session. It is similar to the symbolic C package that we got in version 8, and please have a look at it. It is absolutely powerful. Yeah, we write programs that write our programs. That's the idea behind it. Okay, so now in the second part, I want to show you that we use LibraryLink together with CUDA. And this is what I think really makes it very powerful if you have to write complicated CUDA code by hand, right? Try to keep it simple kernels, then you can use CUDA function load. or try to write symbolic CUDA generation code with this package. If you really need to use a full-fledged IDE, then LibraryLink is the way to go. So I start with an important note. The input arguments to library function load must be in a list even if there's only one argument. That's sometimes overseen. Here's a link to the appropriate CUDA documentation. And now let's jump right into it. And I think the CUDA version of Hello World is vector add, right? You have one vector and you have another vector and you want to add them together. So what I said above here, these are the inputs, right? You see that we have to put them in parentheses, even if we just had one, right? If I removed this, then we just had one argument here. It still has to be in a list. And the output is a real vector. So this is how you specify this. So we have two vectors as input. We get one vector as output. So I have the code here. It's not particularly interesting. I'll show you more in a moment. So now we can just generate these vector lists and add them together. So the comparison is true. What we did from CUDA matches the list addition that we did in Mathematica. Let's totalize these numbers. So there we get a 0. And we can also use libraries that were written for CUDA in the CUDA code itself. For example, Fourier, right? In this example, we are calling the Fourier package in the CUDA package. So let's do some computations with that. Let's generate random reals and let's call our GPU function that is CU Fourier. That's here. That's calling Fourier in the code. And let's compute them with that. So we take these 20 random reals, we apply Fourier on them, and now let's do the return trip. We also have CUDA inverse Fourier here. That's another function in our CUDA code. So let's compare with the built-in functions in Mathematica. So we use Fourier here, and when we ask are they the same, of course we get no, because we're dealing with decimals, but the total is 0. The total of the difference is 0. And I think this is very reassuring that we are doing the right thing here. Okay, another reason why I think it is so powerful to use the LibraryLink infrastructure is that we can now also write additional features in our CUDA code that would otherwise not be possible, not supported by the package. For example, the use of multiple GPUs. So I have a function, and I think this one I should show a bit more detailed here, that I call multi. And the advantage of multi is that I can now write code that uses all of the devices that are available. With the CUDALink package, you can't. You can always set, you can set your device, but you can only set one. But one of the features in CUDA is that you can write code that uses all devices or some of them that you specify. So with this multi-code, I can now write a CUDA code that uses all of the devices by calling CUDA set device. Now I'm not going to go in detail into this CUDA code, but we can use CUDA set device in a loop now. GPU n in my case here is going to be 5 because I have 5, and we set this also with a simple function call. Where is that? Here, CUDA get device count, and we save this in GPU n. And then GPU n is our max iterator, and we can always set CUDA set device. So everything that happens now is per device. Everything here in this loop happens in this device. And a nice way to further speed things up is to use streams. I also don't have time to go into that, but streams are another way to make sure that you make maximum use of parallelism, because that means one part of your code can already start doing the kernel processing while other parts of your code are still loading data. The mem copies are the parts that usually take the largest amount of time. And with streams, everything is asynchronous. With streams, every kernel can totally operate asynchronously from the others, and we have this now in our multiple GPUs. So another advantage also then from this infrastructure is that you can simply print in a file if you want to look at some diagnostic output. I have some fprintf statements in there, and if I execute them, then in a file I can look at what is written into it. Sometimes it is difficult to debug a library because you can't see anything. There are no returns from code in the middle, so you artificially have to create a side effect, and one of them would be to write in a file here that I call test output file. And then I just need to uncomment an appropriate section, and now I can look at my data in the file. Then I can see what's actually happening here in the code based on how I structure my fprintf and based on where in the code I put this. And that's one way to really debug a library that otherwise you're just running from Mathematica, which means you only get the output if you get output. If you have bugs, you don't get output, so now you can never really debug it. And sometimes it is hard to write a main method because you may construct objects that are so difficult and so Mathematica-like that you cannot just create it in a main method in a CUDA program. So I think this is another great way to use the IDE and to look at side effects and to use side effects for debugging. So then here we have the actual launch. Again, we're counting up to CUDA-N. We set the device. We do an asynchronous memcopy. Here is the actual call. Then we copy the data back and then we process it. And here's the part that I said you need to prepare the data to return it through the object that is required for LibraryLink. So here you set it. In this case, it's a real, because I am performing a reduction operation. So in this example, for the multi-kernel example, for the multi-GPU example, I'm using a reducer kernel. So we're adding these elements together in order to reduce from the kernels. I had briefly mentioned in the previous session the reduction operation. The reduction means that we're processing all the independent outputs and we are now bringing the results together in a reduction or joiner operation. And this is what I'm doing here in this reduce kernel function. Okay, what this allows me to do now is that based on how I structure my input data, my request, I can now add a bunch of numbers in a list, and based on what numbers I put in there, I can now perform some very powerful reductions. So my function is called multi-GPU. It calls multi from the file. My input is a one-dimensional vector and my output is a number, a real. So here I'm setting up my function, and if we now want to add, for example, the first n natural numbers, and you see that we had the activity here, we now get them in parallel for these devices, then we get the list of these totals here. So this is the sum of the first n natural numbers. And you probably know the anecdote about Carl Friedrich Gauss as a pupil. The teacher was angry. He said, "What's to the class? Just write down the sum total of the first 100 natural numbers." And 3 minutes later, Carl Friedrich Gauss raised his hand and said, "It's 5050, right?" And he uses the formula that you're probably familiar with, n times n plus 1 over 2. It's also binomial of n plus 1, choose 2. So this is a simple totalizer where I'm giving this table, this list of numbers as an input, and we're computing it across all 5 GPUs. Okay, I don't want to go into all these formulas now. I just want to give you some ideas, some examples to show the value of the totalization or of this reduction. If we're adding n times c together, well then have a guess what that's gonna be. We are obviously getting n times c. And if we do this with a different constant, in this case 2, then we are also computing basically the sum of the sum of c, which is n times c. So here we're getting twice these numbers, 240, 120. Some of these formulas, I just took them from the summation page of the Wikipedia. There's a page about summation, and that contains some of these identities. We are really verifying some identities here. For example, the sum of the first 2i minus 1 is n squared. Okay, so in the first element I give you I squared, that is n squared. It's a different index here. And the other one is the rounded result of the table reduced on multiple GPUs. That's what's happening here. Round of multi of this table, that is 2j minus 1. Right? So we can compare them and we get the same numbers here. So based on these inputs, it seems this reducer kernel seems to be working. We're not restricted to integers. My function can handle doubles. So in this case, the sum of the first log I is log of n factorial. So here you see that I have these numbers as reals. We're not restricted to integers. These columns match. And so forth. I won't explain every one of them. The sum of the first I squared and the sum of the first I cubed. And you'll notice that this is the square of the first i's, right? That's what we had at the beginning. That's famous result in combinatorics. The sum of the first I cubed is the square of the total sum of the first i's, and so forth. Something similar is true for the even numbers, not just the odd numbers. Okay, and you see that it happens fairly fast. It's slower than Mathematica. We can, of course, use these identities and compute it just as fast or faster in Mathematica. But my point is, you can use a multi-GPU feature which you only have from the CUDA code. That's why you need LibraryLink. Otherwise, you would not be able to do a multi-GPU computation. For the last examples, we have to be a bit careful on size. I wanted to show you some large size operations because we do have the ability to use 64-bit integers with LibraryLink. Very big numbers, very big integers. We can use 64-bit integers. That number is this number here. The largest integer we can store in 64-bit integers is 2 to the power of 63 minus 1. So I want to show you some large number examples as well, because that can be done by the LibraryLink code. So how about 2 to the power of n? That's a famous result that the sum of all I element subgroups in a group of n is 2 to the power of n. And the proof is very similar. It's the binomial theorem, and you set a and b to 1, then the formula pretty much stands already in front of your eyes. And you see that we have no sweat computing these numbers with this parallel reducer. Again, it's not better than Mathematica. The Mathematica version is faster and certainly easier, but you can use multi-GPU computation on much more complex and involved things than a simple reducer. Here's another one that goes up exponentially fast. And I have to stop at numbers like 50 or here also 50, because otherwise we get larger than those 19 integer digits. Here's another one that goes up fairly fast and yeah, not restricted to integers. And at the end, I want to show you one big example, and I want to show you that you can use it with real numbers. Again, it all depends on the input vector that you provide. We can, for example, take 1,000,000 samples, a random reel of 1,000,000 samples. The expected value is the middle. So if you use a middle, you should expect something around 500,000. The expected value of throwing the die is 3.5. And that sometimes confuses undergraduate students in their first semester. When a die has only six sides, then they wonder how can it be 3.5? There is no 3.5. But for a uniform distribution, the expected value is the lowest value plus the highest value divided by 2. So for 6, this would mean 7 over 2. So if we do it 1,000,000 times, we get 3.5 million. All right, so here in this case, we should expect 7 million when we go between 6 and 8 and so forth. And a really big example that's really using all 5 GPUs, let's do a multi-GPU on a range up to 100 million, okay? And let's see that we can really see something here in the display so that you can trust me that the GPUs are really busy, and they are, right? You see something here for GPUs 1, 2, 3, 4, 5. Right? You see, it's barely a blip, right? There was barely, time-wise, this was done instantly, barely a blip, but you see that we have green and pink in the first window, green and pink in the second window, and GPU 4 has its own window. We just have the green here. So it was actually doing something, but I needed to do something like a range of 100 million in order to get this giant number here. Okay. This brings me at the end of my session. I hope I have given you a bit of an overview of the CUDALink package, the use of CUDA from an IDE, Insight, the use of CUDA through LibraryLink, and the use of LibraryLink. They all have their advantages and they all have their true value independently and together, right? Using CUDA through LibraryLink just offers so many possibilities and so many tools. It's, I think, the most powerful way to do that. But very often you don't need it. If you just have a clever CUDA kernel, use CUDA library, CUDA function load. Okay, that's the end of my session for today. I hope you had fun. See you next time. Bye-bye.